Hello there. Good afternoon. My name is Vijanth. I'm from University Technology Petronas, Malaysia. The title of the talk is an optimizing camera placement based on task modeling.
Does this work have any coordinates?
Pardon?
Does this work have any coordinates?
Yeah, we have about 6 coordinates. I will name them at later part. Okay, graded risk map is normally used for oil and gas industries. They only will qualify facilities if the equipment flammability index has been drawn such a way that it is actually qualified that all the visual sensors able to detect in a certain distance the fire ignition or the gas leakage at a certain distance, given distance. They have a hazard level of high, moderate, and low. Okay. So this is the equation. Very simple equation they use. They use equipment flammability risk equals to the equipment failure rate and probability of risk, probability of ignition. And you can see the rate means highly flammable and moderately flammable and so on. So the whole idea is when we did this. You see the first one here, this is a software, 3D software that we built for a company called Petronas. Actually, they were competing with Shell at that time, all right? So, and we try to bring now to academic level to whether we can use it for a visual surveillance. So when we first look at visual surveillance, when it comes to image sequence, we found that there are a lot of parameters that we have to look at. We have to see the instance location, we have to see the number of cameras, camera type, orientation of camera can be pitch, hold, and sway, and the quality of measure. Okay, so each camera have a different quality of measure, and from here, which are the variables actually you really want to use, and how you actually going to do the modeling for this. So when you take the very first part on maximizing or optimizing, is actually looking at how you optimize the cost function, actually maximizing the coverage. It has been customary that they used to use a heuristic search, heuristic optimization, normally using local greedy search here, where it's just like you look at the best location, the best pitch, and it can be the best camera type. But if you just reverse the whole thing, best camera type, again the best pitch, and again you get best location and give you a different answer. Then you go to the global greedy search, you look at the best of here, best of here, best of here, you take the best. Well, you get pretty decent. Then you look at if you got 6 cameras that you have to locate, then you don't work. Then you have to use a dynamic programming here. So when last year we published one paper on IEEE sensor on that, only on optimization, we found that that's one problem statement we have found. Then again, there are different way of sensor coverage. These are the things that they use in the literature. The easy one will be just using isolysis triangle, because even these will create a lot of nonlinearity here. Then we have found that on the modeling part, every sensors have their range and a field of view in physics. Okay, and if you see this part here, normally people say this highest field is best. No, that's not the case. Normally when it comes to sensor planning, we do have this for an overlaps, and like this short field of view, we do have high level of coverage at this point here. We come to that point later. And this part here on sensor coverage, actually we actually found that there's an issue here, and that was came on the letters. And the other thing is that on the overlap, every time when you work on sensor planning, they want to reduce overlap for economic point of view. When it comes to oil and gas, that's not the case. It's totally reverse. You need an overlap, because in case of alarm, or when it comes to control alarm, or in terms of maintenance, if you maintain one sensor, the other sensor needs to cover the same area. So the overlaps is important for security, probably not in reverse. You can go from an economics point of view. Okay, what is risk mapping here? So when it comes to risk mapping, his whole idea is that you got a top view, then what you do is that you do a mask, then you grade based on the security need. This is just a toy problem here. He said this is highly risky area. When it comes to oil and gas, we call it highly flammable. When it comes to civilian use, we say highly risk, moderate risk, and no risk maybe. Okay. And the reason we have this for equivalent distance here, when we do mask, if you see the little white space, this is where we can place our visual sensors. Okay, this is just to give you some 3 scenarios. Okay, we have a junction case. Okay, this is where I say the risky area. There's a lot of crossings here. Okay, and same thing for the building. And again, some examples from here, we can say we can place possible placement of camera on these instances. Okay, based on this here, we have, this is just to show you that our service demand modeling, where we are trying to say that when you say, if you look at these numbers here, these numbers are just number that we coined, saying that, okay, we have 3 colors here, sorry, rate, highly, high risk, moderate, and no risk. And we are saying here, all are equal. No, rate are quite higher weightage for rate, higher weightage, moderate, and no weightage for low. Here I'm looking only at the rate as a high weightage. If you look at this sensor modeling here, if you see that this shows that only for rate I'm looking at, it covers all the rate high risk areas. In this, for equal, it covers equally for all areas, and for these, for different weightage depending on the requirement, it covers in different ways. Okay, let's go back to the paper that I wrote recently on this conference. We have done on the risk on the general configuration of camera. Now we are looking at the task. So what's the task all about? The task is now your sensor itself have its grading now. That happens because at this point you can recognize and identify a person. At this point you can actually observe. At this point actually you can detect a person. That's actually the requirement for any video surveillance planning. Okay, if you take up just a small top view of a building, you can say this is my entrance, just like for a hotel here like this. And you can say, I like to recognize people that walk around here. Well, I want to observe, I don't mind anything here because people don't loiter around here. So when you do sensor planning, this is a building, hard building, it's a static object. Then you can see at this point here, I want to make sure that, I can recognize at this point here, I can detect, observe, and the other place, I can just see whether there's a movement of people or not. Okay. For task representation, aim to model sensor vision variation by classifying the field of view based on the details. Here, human or object. Thus, sensitive area requires a close observation where field of view and relatively small focal length generate a recognizable image. So, in this case here, there's a term called coverage effectiveness. There are 3 levels here. There's one metric, it's where you have your so-called your risk map on a static building. This is in your vision task map. So this one is always static, but this one no, because you for different camera, for different orientation, you have a different gradings, and you combine this, you have something in this form. So this is a range of metrics, and you find the best that covers the whole thing. If you look at here, this is not brown, it's actually if a rate covers rate, if you see in color it's brown, and if it's rate here covers with green, so rate here covers with green, we give you in yellow. So that's how it meant. So there's a CE factor and CE map. This is a CE map. A CE factor, actually you have to move around your visual sensor to get the best fit. So this is the result here. So camera placement obtained based on coverage efficiencies. You can see over here, right? So it covers most part of the rate, and this don't have any of those. It's using a normal way of vision without looking at task base. It just don't cover much of those so-called risk areas. If you see that the coverage is very high, it covers very well on the pixel. The coverage here is based on the pixel count, but not on the coverage efficiency. So high in efficiency, we're looking at 4 camera points here, but low in efficiencies, but it actually cover more if you look just by based on uniform grids. Okay, I got 1 minute, I conclude the slide. Okay, every object or even living being have its boundary of interest. Each of them set a hazard trigger based on their own risk measure, which can be probability of risk. The graded risk or task map can be applied in many areas, not based solely on oil and gas, which is very much a close application. Future extension, we will look at overlapping. We don't look at overlapping here. or looking at optimization using dynamic programming here. A similar way of graded map placement of miniature visual sensor can be applied for any machine versions application, or for calibration, for small calibration, or even for docking. So you can just have a different risk map and you make sure you dock properly and you're able to calibrate in a proper manner. Okay, I'd like to thank all my co-authors and also my team, those working with us. Okay, this is the guy actually did all the work, my PhD student just completed his PhD. And this is the guy from oil and gas. He did the project for the oil and gas, which I was the project manager. And this is the guy who said you can use for civilian use. And this is the computational guy who helped me in many things. And these are two guys who program all the software for me for the Petronas 3D fire and gas mapping. And thank you.
The floor is open.